Problem 1 asks you to find the total heat transfer to the balloon and the initial rate of diffusion of helium. The learning objectives included in this problem are heat conduction, heat convection, resistance networks to solve one-dimensional steady-state problems, and steady-state mass diffusions. So the first thing here is the resistance network that includes the heat conduction and heat convection in the learning objectives. Once I know these values, I can plug them into equation 3, the Q total equation, to find the total value for the heat transfer, which is 270.27 watts. Now in the second part, you just use that equation 4 and the parameters given to plug into the equation, and I got a final answer of the initial rate of mass diffusion of helium as 3.98 times 10 to the negative 10 kmols per second. The second problem was a bit more in-depth. The learning objectives here were transient heat transfer in 0-dimensional and 1-dimensional, as well as deriving and solving conduction equations, including boundary conditions and the Cartesian geometry of heat transfer. So in the first part, you had to find the time it takes for the egg to be fully cooked at the surface using a lump sum and 1-dimensional heat transfer equation. In this first part, that is where the 0-dimensional and 1-dimensional transient heat transfer learning objectives came in. So you use equation 1 to find B. This is for the lump sum, and then plug that into equation 2 to get that answer for the first part. And then for the second part, the 1-dimensional, you use the last equations there. The answer differed slightly, which makes sense. Since the BO number was greater than 0.01, you would expect the 1-dimensional approximation to be a better fit. So that makes sense why it has a larger number, as it would take a little bit longer for an egg to become fully cooked. It is quick, but that's just because it's at the surface as well, not the center of the egg. For part B, this is where the learning objectives of solving and deriving the 1-dimensional heat conduction equation with boundary conditions takes place. So you can see the full derivation there. And then once I worked it out that the second derivative with respect to x was 0, I could integrate that twice and plug in boundary conditions to find a general equation for the temperature at any point within the pan that here you're assuming is a large flat wall here, large flat plate. So then once you have the general equation, you plug that in at the midpoint of the pan, which is 2.5 times 10 to the negative 3 meters, and you get a final answer of 122.5, which makes sense because you're starting at the difference between 120 and 125.